steeples. Many passengers believe that an aircraft is simply a large machine with engines powerful enough to fly. But the people
tinting. Inside that silent atmosphere, the young workers barely speak loudly, because every action is connected to a
synchronized. What makes modern aviation different is not that aircraft fly faster or engines stronger, but that every system on board.
The narrow-body aircraft with matte gray metallic surface lying silently in the hangar is actually still speaking through.
If people only see aircraft as mechanical machines, they will never understand why modern aviation places greater importance on data inspection procedures. The white lights reflecting across the matte gray aircraft make the entire space resemble a systems control center. Why are modern aircraft no longer viewed simply as machines, but instead understood as highly complex and tightly connected operating systems?
Under normal operating conditions, every commercial flight is controlled by countless small systems working simultaneously rather than relying only on pilot skill or engine power.
Even the aircraft power supply alone includes several backup layers designed to keep every component operating even if one section unexpectedly fails.
The narrow-body aircraft with matte gray metallic surface does not fly only because of engine thrust, but also because the
young workers inside the maintenance hangar inspect every wire connector and sensor cluster, because even a tiny signal deviation could cause the entire system to react.
On modern aircraft, many mechanical components are actually only the final stage of an incredibly complex chain of electronic control and hidden data systems.
When pilots move the control yoke inside the cockpit, the command is no longer transferred directly through mechanical cables as in early aviation, but is first processed by flight computers.
That means modern aircraft constantly evaluate their own condition before making any major changes during flight in order to avoid dangerous reactions. Beneath the matte gray metallic surface of the aircraft fuselage lie thousands of connections between electronics, mechanics, hydraulics, and software. The female engineer continues checking engine temperature data, while the young workers take turns verifying every inspection step through dual confirmation procedures. The entire normal operating state of modern aviation therefore depends not on the strongest single component, but on the precise coordination of every system functioning together.
But precisely when everything becomes so tightly connected, a major question begins to emerge in the minds of many modern aviation engineers.
If aircraft depend on thousands of interconnected systems, then what happens when just one small signal becomes inaccurate within that entire operational network?
Sometimes an aircraft may have no serious mechanical problem, yet still must be grounded simply because one sensor detects abnormal data.
This confuses many outsiders because they often believe that as long as the engines still operate normally, the aircraft should continue flying safely. The contradiction becomes unmistakably clear when the smallest components on an aircraft can influence the operation of the entire massive flight system. The young workers stop their tasks and wait for confirmation from the lead engineer, because in modern aviation, no one is allowed to ignore a warning. The narrow-body aircraft with matte gray metallic surface remains motionless beneath the white lights, yet inside its data systems, vision. That is exactly what makes modern aircraft completely different from traditional machines, because an aircraft does not operate as isolated.
In modern aviation, the most dangerous problem is not the obvious major failure, but the tiny hidden error silently spreading into other systems before anyone notices.
And from this point, the question in the title moves into its most important stage. What exactly caused modern aircraft to legends? The core reason lies in the fact that modern aircraft are designed so that every system constantly exchanges information with one another.
Even a tiny change in the electrical system causes the central computer to automatically adjust multiple related systems in order to maintain safe operating conditions.
That means engines, hydraulics, electronics, flight controls, cabin pressure, fuel systems, and warning systems do not operate independently, but constantly.
The young workers inside the maintenance hangar behind the terminal do not simply repair failures, but must understand how one change in a single component can create chain reaction. Modern aviation no longer focuses on fixing failures after they occur, but instead prioritizes predicting risks before actual problems appear.
That is why every vibration, temperature, and pressure reading is continuously recorded during each flight, so the system can recognize the
modern aircraft truly operate through the coordination of information between humans, software, sensor procedures, and backup systems. The female engineer continues comparing current data with the aircraft's operational history to determine whether a small change today could become a major risk. Inside that clean and silent environment, every action performed by the engineers and workers shows that what keeps aircraft. Therefore, when modern aviation describes aircraft as systems, it is truly referring to the way technology, data, and procedures are connected. If aircraft were viewed only as traditional mechanical machines, people would assume that maintenance simply means replacing broken parts or checking whether engines still function.
But in modern aviation, the male engineer aged 25 to 30 and the female engineer aged 22 to 25.
Under the white hangar lights, the aircraft no longer feels like a resting machine. It feels like a living system constantly being monitored through every internal reaction. The young workers inside the maintenance hangar behind the terminal are not trained to work individually, but always operate through cross-checking procedures. This creates a major difference between aviation and many traditional mechanical industries, where one component can be repaired independently without greatly affecting the remaining systems.
In modern aircraft, even a tiny change inside control SAR can influence wing responses.
The more advanced aircraft become, the less they depend on manual reactions, and the more they rely on intelligent coordination between automated electronic systems.
That is why modern aviation always prioritizes synchronization over isolated strength, because a harmonious system is far. The narrow-body aircraft with matte gray metallic surface remains motionless inside the clean and disciplined maintenance hangar. Once people understand this, they begin to realize that modern aircraft are no longer simply flying vehicles, but enormous technological.
The future of aviation will not be decided by the most powerful engine, but by the system that understands itself best.
The female engineer aged 22 to 25 continues saving the final maintenance data, while the young workers complete every verification step according to procedure. Inside the maintenance hangar behind the terminal, the narrow-body aircraft with matte gray metallic surface is finally prepared for its next flight. Modern aviation exists because of the connection between humans, data, software, sensors, backup systems. What makes aircraft one of the safest forms of transportation in the world is not that they never experience failures, but that the young workers leave the maintenance area beneath the quiet night lights, while the engineers remain behind to review the entire system one final time.
Aircraft therefore are not simply flying machines, but living systems built upon data procedures and the precise coordination of thousands of elements.